Really, Lashara, you like walked down to the library or went out to your car and signed into the lecture? Just kidding. Oh, what the hell, people? No, you guys were here. All right, write that down. Well, I mean, I don't care if you write it down. So we're talking about blood vessels. And all I was showing you on this, me sitting here screws it up. All I'm showing you is that, this is systemic circulation, right? So the blood goes out to the aorta, then it goes into a bunch of arteries. Then the arteries get smaller and more numerous. Those are called arterioles. Arterioles are really going to just slow the flow of blood down, right? And then the capillaries are super small. I think we did a thing where we were talking about like streets, that like the arteries were like the interstate and arterioles were like Judge Perez, and capillaries were like residential streets, right? And so the arteriole slows down the flow of traffic. Because this is, the artery has a pretty high pressure, right? And then you got to slow it down. You can't put the same amount of pressure that's in an artery into a capillary. So that'll blow it out. And then this is the return trip. So this is leaving the heart and going out to all the tissues or cells, right? And this is the return trip back. So they're using different blood vessels, right? And so they have similarities and then they have differences, right? So we're going to discuss them. And just to recap, what do we call, so if the capillary is like a residential street and the houses were the cells, what's the driveway and the front lawn? What do we call that area? I'm ready. Two things are happening right now. One, pen's drying up. And two, it's super awkward. You guys can't see the sigh on my face, huh? Because of the mask. All right, so anyway, we didn't do the street thing. Oh, maybe that's why. I'm not saying it's like a great thing, but like, we have like I-10, and then that gets to us. So this is the freeway or interstate. It's got like 3 or 4 lanes going in each direction. Everyone's going down at like 80, especially out in the east. Then you go on to 510, which becomes like Paris Road, right? You gotta slow down. You gotta slow down to like, it's supposed to be 40 in front of that school, but you know, we're slowing down to 50. So that's an arterial. There's not many arteries, interstates, right? There's just a few. There are more arterials, but there's not a whole, I mean, compared with residential streets, there's not a lot of Paris Road and Judge Perez and St. Claude. There's not a lot of those streets compared to the residential streets, right? So branching off of this are a bunch of residential streets. Whatever. And then when you go down the residential streets, obviously you get houses. There's all my houses. Those are cells. So if we were using this analogy for the body, these would be cells. And then the cars, in this analogy, the cars, those are whatever, blood cells, red blood cells. And these residential streets are so small that sometimes you can only get one red blood cell at a time. You can only get one car down the residential street, especially when people park on the street, right? So that's like a capillary. You can only get one red blood cell down that capillary sometimes. You can't go 80. You're going to crash eventually because you got to like maneuver in and out of cars and potholes and stuff like that, right? So it's not built to go 80. It's not built for 3 or 4 lanes of cars, right? So that's kind of like this. So you've got these blood cells, and then the blood cells are like cars. There's the houses. The people represent like oxygen. So you get out, the car pulls up in front of the house, you get out of the car, and you go into the house. As long as there's not too many people in the house. So if there's 4 people in the car, and there's 4 people in the house, don't get out of the car. You're going to go to another house. It's too crowded in there. That's diffusion. If there's 2 people in the house and there's 4 people in the car, okay, one person can get out. Because now, when one person gets out of the car and goes in the house, there's 3 people in the car, 3 people in the house, that's equal. If no one's in the house, 2 people are going to get out of the car and go in the house. You're going to make it equal. But that's actually not the thing is that this space, all this space in between, all this space here in between the house and the street, we call it interstitial fluid. So this is all in green here. This is all interstitial space. We call it interstitial space, and there's fluid there. There's like water there. It's called interstitial fluid. Right? So the capillary is like the street. Driveway, the grass is like the interstitial fluid. The house is like the cell. Right? And then, so the thing is, inside the house is carbon dioxide, right? So the carbon dioxide, they're also, what the fuck? Let's call them like animals, right? They're dogs. They're inside the house. As the people are going, as the oxygen's moving into the cell, carbon dioxide, like the dogs are running out of the house and getting back into the car. And they follow the same rules. Dogs follow the same rules. If the car is filled with dogs, they're not going to get in the car. They're just going to hang out in the cell. So they're only going to get into empty cars. So carbon dioxide is going into the cells because it's empty, there's no carbon dioxide in the cells. And oxygen is jumping out and going into the house, into the cell. I'm probably making this confusing at this point, but they're taking different roads. Here we talked about artery, arterial, and then all these little capillaries, right? So artery, arterial, capillaries. Now coming back, they take like different roads. So for me, to continue the analogy, I'd say like these are like, nobody has them in New Orleans, but like, you got like roads in the back of your house where like the garbage trucks use, like alleys. We don't have them here, but like parts of the US, you've got roads in the back of the house. So, like delivery trucks, garbage men, sometimes we use them, right? But the street where the kids used to play, that would usually be empty of cars because everyone's using the alleyways, right? So you take the alley, you take that down to the service road. The service road's like the vein. So I can get all the way home using service roads, right? I'll just take it all the way through the east. And then I'll, I don't know what I'm going to do. Get how it works. Then I got to cut over by the lake or something. But anyway, you get my idea, right? So like an alleyway, a service road, using different roads, right? A service road and a freeway, they're different, but there's things that are similar about them, right? So when you look at an artery and a vein, like in a body, they look a little bit different, but there's also things that look the same, right? They've got like layers to them. When you look at like an interstate, there's like the asphalt, and then there's like the gutter on the side, and then there's like some grass, right? So there's like layers to the interstate. Same thing with an artery, it's got like layers to it. So, all right, I'm gonna erase all this stuff. So what we're gonna do is talk about each of these. We're gonna talk about these 5. So we're gonna talk about an artery, an arterial, capillary. I'm not gonna say much about arterials, to be honest, so I'm gonna talk about arteries. I'm gonna just skip over this because they're just little, they're like little arteries. And then I'm gonna talk about capillaries, and I'm not gonna really talk about venules, but I'm gonna talk about veins. So, but anyway, that's kind of how it goes. So from an artery to an arterial down to a capillary. Now this is the return trip. A venule is like a little it's kind of like a capillary. It's like a miniature vein. So, and just to remind you, arteries are, anything going away from the heart, and the venules and veins are going toward the heart. Because remember, when you're talking about lungs delivering, like in the case of the lungs, it's a pulmonary artery, but it's deoxygenated blood. But in any event, it's going away from the heart, it's going to the lungs. Let's talk about arteries. So arteries have three layers to them, like 3 coats, right? So coats we call tunics. So tunica meaning like tunic, like coat, right? So it's got 3. So the most internal one is called tunica interna, or tunica intima. Your book might call it tunica intima. And then media is the middle, and then externa. So not too difficult of words. Tunica interna, tunica media, tunica externa.
We can't see the board.
I know. I'm going to fix this right now. We both have needs. You need to see the board. I need to sit my ass in front of the board. Can you see it? Yeah.
No.
I can see it. Really? see this. Liars, you're just trying to make me stand up. All right. So, 3 layers. Better I stand up because I'll put myself to sleep. I'll just be sitting there talking and then I start like dozing off because it's so boring. I bore myself. Like, oh, who's talking? Fuck, you're talking. You're so boring. And then while I'm thinking all this, I'm like saying these words, and I don't know. And I start getting tired. I just gotta stand up. I don't know how you guys do it. I know how you guys do it at home. You're on your social media right now. You've got me on the background. That's how you do it. All right, so where are we? All right, so there's different things that we're going to put in arteries. Muscle and elastic. Right, so arteries have to do 2 things. They got to be able to stretch, be stretchy, because that blood's surging out from the heart. Right, when that blood comes out from the heart, it's pressurized. The ventricles are squeezing and pushing that blood out of the heart. So it's got some pressure. So these arteries need to be stretchy. So there's a lot of elastic in arteries. But it also has to be able to constrict. So it's got some muscle in it. So let's start with the most internal layer. The first thing that I would ask you is what's the tissue called that lines your anything? Tissue lining. You should give me a word that you learned last semester in AMP 1. Right at the beginning, and I know Mr. Waddell taught it to you if you took him. And you learned it in Biology 1. And I told you all this would come back, and you didn't listen to me in Biology 1. Those of you that had me. The lining, any tissue that lines, starts with an E, any tissue that lines anything, epithelial, epithelial, epithelial. If you're a nurse in a hospital, you're going to hear the word epithelial all the time. In the blood vessels, we call it endothelium. That's like an exception we make, but it is epithelial. In fact, I even used the word last class when we were talking about blood clotting. Endothelium, the endothelial tissue, aka epithelial tissue. So, the lining of the blood vessel is epithelial tissue. There is some elastic. So we call it elastic lamina. Elastic tissue is just like a form of connective tissue. So we have elastic tissue in there, and something else. It's obviously not too important because I can't think of it. But there's a third thing. It's kind of bugging me because I gotta have 3 of something, but whatever. It's in my lecture. It's in the other video. So you've got some endothelial tissue. You've got some elastic. Tunica media. That's muscle and that's elastic. So we've got smooth muscle, which I might be calling it muscularis, but it's muscle, and then we have elastic. And let me just do this one. That's what people do when they don't care and they don't want to think about it. They put CT. CT stands for what? Connective tissue. So I'm sure if I looked it up in the book, I would have some kind of better answer, but I don't care about this outer layer. dense connective tissue, I mean, who cares? But let's talk about this middle layer. So this tunica media has a layer of muscle and a layer of elastic. How thick they are depends on where it is. So you actually have two different types of arteries in your body. You have arteries that are muscular and you have arteries that are elastic. Muscular arteries, we call them, another name for them is distributing arteries. I spelled that right. And then elastic is called conducting. So distributing arteries have a very thick muscle layer and a very thin elastic layer. And they are found further away from the heart. The heart. These are found closer to the heart. So arteries that are closer to the heart, the tunica media has a thicker elastic layer. And arteries away from your heart, so down in your legs, your arms, those are muscular arteries. The arteries in your thorax, let's say the subclavian artery around your shoulder or whatever, they are conducting arteries. They have a thick elastic layer and a thin muscle layer. You do not want to constrict or contract the muscle in your subclavian artery because it's like coming out of your heart. Right? It's that ventricle is pushing the blood out of your heart. Here it comes around your shoulder, and then you're trying to constrict the lumen. You're trying to make it smaller. You're going to screw the heart up. Not only do you not want to constrict it, you want it to be more elastic-y. You want it to be able to, because that blood's like surging in it, so you want it to be able to stretch out a little bit, right? And then even when the elastic snaps back, that pushes the blood further through your body. That's why we call it conducting. So it stretches out, and then the fact that artery goes back, that helps to push blood through the body. However, in your, here, let's say the artery, and they're to give you a crash course to artery names. Most of them are named after bones or positions, like antecubital and cubital, or you just find the bone. So if I'm going here, I'm I don't know what that artery is. I'm just going to think, well, what's that bone here? And then I would think, oh, I know that bone. It's the, is that bone here in your forearm by your thumb? Your thumb turn? You guys don't know the bones? Yes, you do. Because you don't want to talk, huh? None of you guys want to talk. Radial bone. So anyway, they're named after so that'd be like a radial artery, right? So anyway, the radial artery, that's a muscular artery, right? It's not surging here, not necessarily. But I want to be able to, what if my arm gets cut off? I want to be able to, let's think of something better than, more practical. But if my blood pressure drops, right, you're going to die because your blood pressure is dropping. You don't need to get blood to your hand. You can wait for 10 minutes. So I want to constrict those blood vessels. I can give a shit about my hands and feet. I need to get that blood here, really here to my heart. So I'm gonna shut down my appendages, and I'm gonna keep that blood in the core, right? Or you could say if you cut your hand or something and you're bleeding, you can constrict those blood vessels, and so you don't need a lot of elastic there. But you don't want to constrict blood vessels around here. That's going to mess you up. So anyway, that's two types of arteries. So let's talk about, and so the labs are covering like the names. You should know you should know some of the big arteries, right? Your carotids, your subclavians, you need to know like the big ones. Femoral, stuff like that. Stuff that you might come across in practice, right? And a lot of the veins, not all of them, but a lot of them have similar names. For example, subclavian artery going around clavicle, right? It's underneath the clavicle, subclavian artery, and then also the vein coming back is also the subclavian. All right, so as you're going through those labs, I know a lot of you finished it already, but just at least become familiar with some of the major names, right? This is what kind of pulse is this? What kind of bone is this? Y'all suck. You don't want to talk.
Radial.
So what kind of pulse would this be? Radial pulse. What about this one up here? What artery am I pushing on?
Carotid.
And they're like practical things, right? Those are two things that you would come across all the time if you do anything in the medical field. Taking a pulse at the carotid versus radial versus pedal. I was trying to lift my leg. I wasn't doing too good at it. And I was trying to, if I were to go further, I'd try to point to my foot. But, okay, so yeah, try to remember all the names. So this is arteries. Arterioles, I'm really not going to say anything about them. Just that the point of arterioles is to lower the pressure. Or we could say increase resistance, because that's kind of like that's an important topic for this particular chapter, resistance. So resistance meaning I'm slowing blood flow down, right? The fact that you take something that's 4 lanes and you bring it down to 2 lanes, what does that do to traffic, right? It just, all of a sudden there's just massive traffic, right? Because you're slowing everything down just by taking out 1 lane, right? It's just, I don't get it. They close down just 1 lane out of like 4 and everybody's at a stop, right? So that's resistance. Now you're slowing down, right? Same idea with your blood vessels. So that's what arterioles do. They slow down the pressure. And they're slowing down the speed of the blood, but they're slowing down the pressure. Because you want to get it to a capillary. Capillaries are what are feeding the cells. Right? The capillaries are like our residential streets. So the capillaries are what are feeding. There's tons of them, right? To give you an example, if you gain a pound, you're also gaining like 200 miles of capillaries, miles around there. But it's around there, 200 miles of capillaries with 1 pound, right? So they're really tiny. So you cannot see them, right? Can't really see arterioles hardly. You'd have to really look. Arteries you can see. If you're dissecting something, you can see it. I can see all my arteries. Like if I'm dissecting a person, I can see all their arteries. It's very easy. Some arterioles, because you can see the arterioles branching off of the arteries, but you're not going to see many of them. So capillaries are feeding this is where exchange happens. This is where oxygen's leaving the blood, or fluid. This is where fluid's leaving the blood. And so, or this is where things are going into the blood. So there's 3 types of capillaries, and the first one's called continuous. A continuous capillary, meaning like there's not a lot of space for things to get in and out. There are things, for example, where one cell meets the other cell, there'll be like a space in between those 2 cells, which we call an intercellular cleft. Or maybe it's called intracellular. I don't know. But you know, it's right where you have, right where you have the space, like usually endothelial cells or epithelial cells, I think of them like apartments, right? They're right up on, or condos, they're right up on each other, right? There's no space between them. But sometimes with these, so this is like they're supposed to be going like around. These are like endothelial cells. They're all touching and they're making like a ring around, right? But there's some of them there's some spaces in between them. Or there's just like, they're touching, but you can see how something could just kind of move across, like move in between the cells. And so we call these intracellular clefts. They're not like big spaces to let things through. And you'll find these, like, for example, your brain, up in your brain, you can have a lot of these. Then the next type is called fenestrated. They have larger intercellular clefts. So the spaces between the cells are even larger. And they've got pores. These capillaries have like pores in there, which we call fenestrations. I think it means window. It's like Latin for window. So, larger intercellular clefts, fenestrations, you would find these like so now you can move more stuff in and out of the capillaries. So if you think about places in your body where things are going to go into your blood or out of your blood, I would think of like endocrine glands. Maybe around my thyroid gland, because I'm making thyroid hormone and I'm putting it into the blood. So I would need bigger spaces to get it into the blood. Or I'm pulling iodine out of the blood, so I need bigger spaces, right? Things are moving in a big, I'm moving more stuff in and out. And then the next one is called sinusoid. And those move even more stuff in and out. There's like, and I'm not going to write it here, but there's like gaping holes, huge intercellular cleft, just massive spaces, and huge, again, fenestrations, big pores. They're so big that they can fit a whole blood cell. You can get a whole red blood cell that can go in and out of these sinusoid capillaries. So where in your body would you have a whole blood cell go in or out of a capillary? Knowing what you know about red blood cells. So you just think, where are they made? Where do they die? Where are red blood cells made?
In your bones.
Yes, good enough. I'll take anything. But like red bone marrow, that you'd find sinusoid capillaries in your red bone marrow. Where do they die? Where are they phagocytized? Liver and spleen. Yeah. I know you know it. Some of it is just you're waiting for someone else to answer. All right, so yeah, that'd be an example. Your liver, your spleen, you have sinusoid capillaries. Your liver is making all sorts of shit and throwing it into the blood, and vice versa. It's taking stuff from your blood and processing it, right? So sinusoid capillaries. So continuous, not a lot of spaces for things to go in and out. Fenestrated more. Sinusoid is like the most. Huge intercellular clefts, huge fenestrations. Feel free to use any adjective or adverb you want. Massive. So, all right, since we're on capillaries, let's talk about how things go in and out of. Well, we know that things go in and out because of spaces. But what is it that's like forcing things, like why, how does fluid get in and out of a capillary? Well, there's things that push fluid out, and then there's things that pull fluid out. So there's a push factor and there's like a pull factor. So the first answer is diffusion. That's how things get around your body in general. How does oxygen get from your lungs to your pinky toe? The short answer, diffusion. Diffusion, diffusion, diffusion. Higher concentration to lower concentration. That's how stuff gets around. Higher to lower concentration. I was talking about, probably confusing you, talking about 4 oxygens sitting in the car, and if there's 2 oxygens in the house, but I was doing diffusion. You go from higher density to lower density, more crowded to less crowded. It's diffusion. That's all this stuff Margaret Orr's doing. She's going like this and like this and like that. It's all going from the H's to the L's. We have a high pressure from, I don't know what it all means, but that's what she's doing. The high pressure is going to come to the low pressure. Is it cold where the H is? Is it warmer where the L? Okay, then that cold is coming to us, and that's diffusion, right? And then when fluids, we have a diffusion of fluid, like water, we call that osmosis. That's how water diffuses. The diffusion of water is called osmosis. But remember, water is a little bit different. We have to consider something else. Water follows solutes. So remember when we're talking about like antidiuretic hormone and aldosterone, like it was about sodium, for example, not so much with ADH, but with like aldosterone. When you keep salt, you keep water. So water likes to go wherever the salt is. Water likes to go also where the albumin is. So albumin is going to make a difference in here. All right, so when fluid leaves a capillary, we call that filtration. That's leaving a capillary, going to the interstitial fluid. So that's water leaving the street and going into the driveway or whatever. Okay, that's filtration. And then going the opposite way, we call that reabsorption. I know the words don't fit exactly, but filtration, fluid leaving a capillary. Reabsorption, fluid going into a capillary. So the question is, what is making fluid leave a capillary, and what's making fluid go into a capillary? For here, there's 2 different pressures. There's something pushing fluid out, and there's something pulling fluid out, or drawing it out. Pushing it out is blood hydrostatic pressure, which is really blood pressure. That you don't really even need, well, you need the word hydrostatic, but I mean, between you and me, you don't. I mean, your blood's pressurized, right? It's got pressure. So your capillaries have some pressure to it. That's pushing fluid out. What's drawing it out? Albumin. We call this interstitial fluid osmotic pressure. Which I spelled wrong already. Interstitial. The word's harder than what it is. The fact that it says osmotic tells you something about fluid. Well, fluid tells you it's fluid too, but it tells you water, right? Water, something about water, and osmosis meaning something about higher to lower, or something about water moving, and then interstitial, interstitial fluid is going to tell you where. So here's like here's a capillary with all the whatever. There's some blood cells. We don't care about blood cells. All right, these dots are going to represent albumin. So there's some albumin in the blood, but here there's like a lot of albumin in the interstitial fluid. So there's more albumin in the interstitial fluid. Water wants to be wherever there's more albumin. So that's it. It's kind of pulling the water out. So that's what interstitial fluid osmotic pressure is. You're making a pressure to cause osmosis. The albumin's making the pressure, and it's drawing the water out. But I could do the opposite. Over here, there's more albumin in the blood. That's going to do the opposite. So here the water's leaving, right? The water's leaving the blood. As the blood flows, now it's the opposite. Water's coming back in because there's more albumin inside. We call that blood colloid osmotic pressure. That's kind of like lame words, but it just depends. More albumin in the blood, we call it blood colloid osmotic pressure. More albumin in the interstitial fluid, that's interstitial fluid osmotic pressure. That's reabsorption. That's pulling blood back in. So we've got two pressures pushing fluid out. I keep saying blood out. We have two pressures that cause fluid to go out, filtration. So there's two pressures behind filtration. There's one pressure behind reabsorption. Your book might talk about a second pressure. It doesn't have any bearing. I don't know why your book is talking about it. It doesn't do any, it's not a factor, so I just excluded it, right? So yes, there's technically another one. It doesn't do anything. So there's one fact, there's two pressures, right? Your blood pressure, just the fact that your heart's beating, that's creating blood pressure. Two, the albumin in your interstitial fluid. What makes fluid come back into your blood? Albumin in your blood. That's drawing the fluid back in. So filtration is fluid going out of your capillary. Reabsorption is fluid going back into your capillary. Oh, we're almost done. Any questions on this? I definitely want you to know filtration and reabsorption. What are the pressures driving filtration and reabsorption? What happens if I have too much filtration and not enough reabsorption? That means I've got water leaving my capillaries and going into my interstitial fluid and not enough going back. What would their feet look like? Or hands or something? They have a lot of water in it, right? So it'd be all swollen. You could give that person albumin and put it into their blood, and then that would maybe draw some of the fluid back into the blood and make the edema go down. Yes. So, yeah. And that actually happens. We have both of these going on, but the problem is our body does more of this than it does of this. But we have there's another system, the lymphatic system. Our lymph picks it up. So that's for a later chapter. But right now, filtration and reabsorption. I'm going to erase this. So now we'll talk about the return trip. What do I want to talk about? Not venules. Talk about veins. Veins kind of look like arteries, but they're different. They have all three layers, meaning they have a tunica interna, a tunica media, tunica externa. I didn't tell you this, by the way, and it's not like, I'm not going to ask you on the test, but a capillary doesn't have a tunica media, it doesn't have a tunica externa. All capillaries are, it's epithelial tissue, and it's like a basement membrane around it. That's all capillaries really are. So, but veins have a tunica media, tunica externa, tunica interna, but there's different stuff in it. So for one, there's no elastic. Not really. I'm going to say no. Not sure if I'm exactly right on that, but maybe. You know what, I'm just going to cover a little bit of elastic. That will cover my ass. And I'll say not much muscle. You don't need either one. There's not a lot holding its shape. When you look at an artery, like in a cadaver, it's round. Like it's like a tube. When you look at a vein, it's completely flat. That's how they exist. You know, as long as there's not like blood coursing through it. But even when there's blood coursing through it, it's not like, you know, it's just sort of flat looking. It's never like a pipe, right? You don't need elastic and you don't need muscle in veins because the difference of pressure is so great between them. So an artery, so when we measure pressure, we always measure pressure in millimeters of mercury. That's what that stands for. They still use it. mmHg, millimeters of mercury. When we talk about the respiratory system, we're going to talk about this again because we're talking about air pressure. Here we're talking about pressure of your blood vessels, right? So your artery, right when it comes out of the heart, an artery is like around 110. Think about your blood pressure. It's like we use the number 120 over 80, right? That's the pressure, right? So we know coming out of your heart, it's somewhere around 100, 110 or something like that, right? Then it goes from an artery, it goes into an arterial, then into a capillary, venular vein. By the time it gets into a vein, it's like 10 to 15 or something like that. So it's a huge difference. It's only 1/10 the pressure that it was before. Remember, every time it gets smaller, you're forcing it to go from an arterial to a capillary to a venular. It's got to slow down each time. So by the time it gets into a vein, yes, a vein is bigger than a capillary. It's like it's wider, right? But it doesn't matter at that point. The pressure's already been dropped. So it's way down. You don't need elastic because there's not blood surging into a vein. It's just trickling. When someone cuts their vein and someone cuts their artery, it looks different. The artery, first of all, I don't know why I'm doing this. The artery surges blood, right? It pulsates. It's like on TV, kind of. I'm going like this because I've seen it on people's arms, right? If somebody's shunt blows out, the blood will, from here, it'll hit the wall, right? Or I'm going here because I'm thinking of sometimes heroin addicts, if they get gangrene or something, in their arm, and if it reaches down to the artery, when they go to touch something, it hit the wall. But it's like that, right? It's like on TV, like you'd see on a horror movie. And it's like a brighter red, well, that doesn't matter. But a vein, it oozes out, right? It might look like it's really traumatic, and it is, but it's not like spraying out, right? There's a difference because the pressure is so different between the two. So you don't need muscle, not a lot really. You don't need elastic. You just need something to hold that blood until it makes it back to the heart. A lot of veins will have valves. Because think about it, this pressure is low. Not only is the pressure low, but how's all that blood going to get up my legs? It's like low pressure, and my heart is making it come up. So my heart is beating, and it's making all the blood go down the arteries to my feet. And then it's also powering the return trip. So that's a lot of work. So your vein, this is the vein coming up from my leg, right? And the blood's moving that way. You'll have valves, right? So the blood moves across the valve, and then if it tries to turn around and go back, down with gravity, it's going to close the doors of the valve, and then that's it. It won't get through. Sometimes these valves get screwed up, right? And then you're going to get, they won't open right. And then that's why these things bulge out. You get a varicose, varicose veins. But anyway, they have valves. Veins have valves. Arteries don't. No need. Oh, all right. Next class, I'll pick it up talking about a couple of ways that we have to get blood up our legs because it's low pressure, right? So we need some other ways. Does anyone have any questions? Okay, I'm going to stop recording. Thank you, Ashley. You're listening.